Good morning, students. In this video, we shall discuss about the multiplication of signed numbers, that is using BOOTHS algorithm. In the previous video, the link has been shared in the description. In the previous video, we had discussed about the multiplication of two unsigned numbers where we will not be considering any symbol for the numbers. Let us assume I'm going to multiply two numbers. For example, it will be -5 multiplied by +8. So here in this illustration, we are going to multiply two numbers in which we are considering the whether it is a positive number or negative number. So here -5 is a multiplicand and 8 is the multiplier. So as mentioned in the previous normal multiplication, in the multiplication of the unsigned numbers, multiplicand will be stored in the B register. I mean -5 will be stored in the B register, and then multiplier will be, multiplier values plus 8. This value will be stored in the Q register. So here, surely we have to make use of the use complement of P. So I will be explaining where it will be used. So what will be the value for the -5? What will be the binary value for +8? So one thing we have to remember is in the signed number representation, the MSB position, the most significant position will be the representing the signed value. So we can write the binary value for the -5 as -5 can be represented in 3 bits also, and can represent 4 bits also. It can be represented 5 bits also. For example, 2 power 0 is 1, 2 power 1 is 2, 2 power 3 is 2 power 2 is 4, and 2 power 3 is 8. Suppose if I am considering this, this representation for representing -5 means it will be for -8. So this MSB will be -8, and we can represent the value as, since it is a minus, this must be taken 1, and this is -8, but I want -5, so +3. So -8 plus 3, I will be getting this as the value as -5. But if I want to represent this 8 in terms of the same representation, I have to make use of here. Without this number, I can't able to mention 8. 4 plus 2 is 6. 6 plus 1 is only 7. So I have to go to the one more weight that is called as 16. I mean 2 to the power 4 it should be 16. That should be -16. And as a chain, it should be +8. So the most significant bit MSB will be 16. So we have to represent -5 also in terms of 5 bits and 8 also in terms of 5 bits. So -5 in terms of 5 bits is -16. So here it should be definitely 1, because since it is a negative number, I should make this as 1 and -16, but I want only -5. So I have to reduce 10 values. Reduce 11 values. So 1, 8 plus 14, 10 plus 1. So the value for -5 is 1, 1, 0, 1, 1. The value for +8 will be 0, and here it will be 1, 0, 0, 0. So the value for +8 will be 0, 1, 0, 0. So since the MSB is 0, we can tell it is a positive number. Since the MSB is 1, it is a negative number. So now we can. So now the value for this multiplicand -5 is as we determine it is 1, 1, 0, 1, 1. And the multiplier value, the +8 is 0, 1, 0, 0, 0. So we are initiating the process here. So here, let me get the summation. So as a first process, we have to initialize certain registers. Here also we are using registers like a register, and we are using B register for this multiplicand. So here I'm using the register name is B. You can also even use it, name it as M also. That's your wish. So multiplicand register to store it in the B register, and then Q register we are storing the multiplier value. So here I'm using A register, and then here I'm using Q register. In the previous multiplication process, multiplication of unsigned numbers, we had considered one more register called as carry, but here there will be no carry, because since we are taking 2's complement, in 2's complement methodology of subtraction, if carry is generated means carry should be discarded. So here there is no need of carry register. Instead, we are taking one more register called as Q -1. So this -1 should be the substitution value. So this q minus 1. So this entire thing will be q minus 1. So during the initialization process, all the accumulated bits should be 0. So all should be 0. So 0, 0, 0, 0, 0. And in Q register, we'll be storing the multiplier value. What is the multiplier value? 0, 1, 0, 0, 0, 1, 0. And in Q minus 1. So look at this one. In Q A also, I have to store is 0. In Q minus 1 also, we have to mention as 0 during the initialization process. And what about the count is? Count is, as I mentioned in the previous algorithm, that is, count is the number of bits in the multiplier. The number of bits is 5. So here also the number of the count should be equal to 5. So after the initialization process, we are going to check the two bits, that is Q naught. This is the Q naught position, Q naught and Q minus 1. These are the two bit position we have to check. So we have three conditions. If Q naught and Q minus 1 are same, I mean, if Q naught and Q minus 1 are 1, 1 and 0, 0, no process will be performed. Just shift right, just right shift all these values. And if suppose if Q naught is equal to 1 and Q minus 1 equal to 0, I mean, both the values are seen to be 1, 0, then we have to perform A minus B register. I mean, A minus multiplicand value. If the value of Q naught and Q minus 1 is 0, 1, then we have to perform A plus M, I mean, multiplicand, or here we have taken as B, so A plus B. After performing this one, we have to once again right shift, and this process has to be repeated for the n number of terms. In our algorithm, I mean, in our scenario, we have to take 5 number of counts. So this is 5 bits, so count is equal to 5. So as a first process, I am checking what is Q naught value. This is the Q naught value, and this is Q minus 1 value. If both the value are same, I mean 0, 0, just shift the values towards the right side. No need to perform addition or subtraction. So just right shift. So this 0 will be given here. This 0, I mean, let me use notation. This 0 will be given here, and this 0 will be given here. This 0 will be given here, and this A value will be given here, and this value will be forward to the Q minus 1. So like this, right shifting will be done. So here it will be 0, 0, 0, 0, 0. 5 zeros of A has been stored, and the Q value is 0, 1, 000. So 1, 0 will be shifted to Q minus 1. So now we can observe the MSB portion of A is empty. We have to fill. So what data we have to fill is the data which has been in the MSB has to be shifted. At the same time, the same value will be forwarded, and the same value will be stored in the same position also. So I repeat, the MSB portion will be shifted. Also, the MSB value will be stored in the same position also. So here I'm making it as 0. So this is the first count. So what we have done is just we have performed right shifting process. So before that, this is the initialization process. After initial process, we have made A equal to 0 and Q equal to multiplier value. So first is Q equal to first cycle has been over. Now total count is 5. I have performed only one count. So once again perform. What is the value for Q naught and Q minus 1? Q naught is 0, Q minus 1 is 0. If both are 0, I have to perform just a right shift. No need to add or subtract. So just perform right shift. The 0 will be given here the same, and the same 0 will be forwarded to the next position also. Right shift, and this value, let me annotate here. So this 0 will be given here, this 0 will be given here, this A will be given here, and this Q will be given to Q minus 1. So here 0, 0, 0, 0. And here, what is the Q value? 0, 0, 1, 0. So 0, 0, 1, 0, 0. This Q minus 1 portion value will be discarded. So once again, here I perform right shifting process, and this is the cycle number 2. Where the cycle has been over? No, it is 5. So once again, I have to perform the this checking process. Q naught equal to 0, Q minus 1 equal to 0. So if both the values are 0 means, once again perform the right shifting only. As right shifting, so here I'm performing 5 zeros here, and here 0, 0, 0, 1, so 0, 0, 0, 1, and here this 0 will be shifted here. So this portion has been empty. So what I mentioned, the same 0 will be shifted here also. So we have completed the third cycle also. Just perform the right shifting. Now check this value, Q naught and Q minus. Next 1, 0. if the value, if Q0 and Q1 minus 1 is 1, 0, we have to perform A minus B. I mean, B in the sense multiplicand value. Minus, I mean, subtraction cannot be performed. So we have to perform the 2's complement of this P, 2's complement of this P, and we have to add it to the A. What is the 2's complement for this one? So from 1, this MSB will be as it is 1. And then, sorry, this LSB will be as it is 1. Remaining values will be 1's complement. So here it is 0. If it is 0, it is 1. If it is 1, it is 0. If it is 1, it is 0. So this is the 2's complement value for the given B register 11011. So we can able to even check this value. So this is a 2's complement value that is. So what it done is it's a shortcut method. The LSB 1 will be as it is 1. Remaining values will be performed 1's complement. That will be the 2's complement. So this is 00101. So now what we have to register A value plus 2's complement of B register. So what is the A value 0000 plus 00101 will be. So A register value will be 00101. So let me clear these annotations. So 00101. And then just shift all the, then just use all these Q values as it is. Don't perform any movement, and then Q minus 1 also as it is. So what we have done here is A is to A minus B we have done. That is A plus 2's complement we have done here. So after this one, that is after this performance, that is A equal to A minus B, we have to once again perform right shifting of the existing bit. So right shifting is 0. I'm taking this value 0. I mean 00101. Here right shifted, and what is the value here? Q value is 0000, and this one will be transferred here. So what we have done is right shifting. So these two processes will be coming under the fourth cycle. Whether the count is over? No, one more count is there. So this A value is empty. So I'm just answer this using the same value of MSB. Now check what is the value for Q0 and Q minus 1. It's 0 and 1. If it is 0 and 1, we have to perform A plus B. A plus B in the sense normal value we can use 11011. So what is the value for A here? Value for A is, let me use annotation. Value for A is 0, 0, 0, 1, 0. So this is A value. This is A value. And what is the and what is the B value here? B value is so now we have to perform A plus B. So I have taken this. Now let me take this one 00010. Let me use this up here. And what is the B value? B value is 11011. So add these two numbers. What will be getting? Adding these two numbers, this will be 1. This will be 2. So 0 with carry 1. So carry is anything here 1. This is 1 and this is 1. So we'll be getting 11101 will be the answer on performing A plus B. So 11101 will be here. So use the same value of Q here. Use the same value of Q. Use the same value of Q minus 1. Sorry. Use the same value of Q minus 1 here. So after performing this addition process, we have to once again perform right shifting. So right shifting in the sense, these values will be coming in 1 here, 1 here, 1, 0, 1, and Q is 1, followed by 0, 0, here 0, this 1 will be discarded, and here the same one will be performed again. So this is the count number, count number 5. So now what we have done is here A is to A plus B we had done, and here after this one, we have performed the right shifting. So all the count is over. Now this A and B, A and Q register will be together forming this, together forms this result, together give the result. What is the result here? Is 2 power 0. So 2 power 0 is always 0. So what is the value? This is 8. We have taken 8 here, and we have taken 16 here. So we have taken 16, and we have taken, there is no 32, and we have taken 64 here, and we have taken 128 here, and we have taken 256 also, and we have taken minus 5112 also. So on performing addition and subtraction process, we will be getting the answer as minus 40. So what should be the answer here on performing 5 into minus 5 into 8, we'll be getting minus 40. So the result is minus 40. So that's all that's how the multiplication of sign numbers has been performed using the BOOTHS algorithm. Thank you.